Hello, students. We
Hello,
are
friends.
we are looking at the activity true to form, and both of us are very true to form because we are awesome.
Well, one of us is. I don't know about
Yeah,
the other one.
yeah. We'll let you figure out which one we're talking about there. So we want to talk about the axis of symmetry of each quadratic function. This is going to be based on the moving graphs into different groups that we had last week, and in looking at these different types of equations. I'll take a look at the first one, Mr. Butterworth.
That sounds great.
So we've got f of x is -4, x minus 3 squared plus 2. One of the things that I noticed from the work that we did last time is that this is something called vertex form. And oh, look, vertex is a key term for us. And one of the things we talked about in last week's activity was that we could find the vertex based on identifying some points here, and that's going to be our x and y values, 3, 2 for my vertex. And that means my axis of symmetry, my x of psi, is going to also go through this. So if we've got a parabola at 3, 2 with my vertex.
Except Mr. Butterworth drew it correctly because it's supposed to be facing down.
Oh, that's totally true.
I was trying to help you out and draw the picture.
Well, I appreciate you. I will use your picture. So we've got 3, 2 there. And the axis of symmetry is going to be at x equals 3, because that's our vertical line that makes it foldable.
I agree with that. All right, let's see. I'm going to look at the second one. I'm glad I don't have to look at the third one. That looks scary. So the second one is in factored form. So that's this one here. If you think about that, g of x equals 2. I got confused because I couldn't see the bottom of the equal sign, so I didn't know if that was -2. X plus 5, x minus 7. Well, if I think about what makes x plus 5 0, that is -5. And if I think about what makes x minus 7 0, that is 7. This is a parabola with a positive leading coefficient, so that's going to look something like this. Now, parabolas are symmetrical. So what you can do is simply go right in between 5 and 7. So back in geometry, you may have learned how to find the middle of two numbers. You just add them up and divide by 2. So -5 plus 7 is 2, divided by 2 is 1. So this point here is going to have an x value of 1. The equation of the axis of symmetry is going to be x equals 1.
All right, for the last one of these, 4x squared plus 6x plus 1, our expectation would be that you would graph this on Desmos, and that you could use Desmos to click on the vertex, and that would tell you what that point was, which would then give you the axis of symmetry. We may have talked about this last week. I don't remember while I'm recording this video, because for us, last week is in the future. It's a whole time travel thing. It's a mess. But I think in this set of notes, we're also going to talk about a formulaic way to do that, which I don't love. But we can use a formula, x equals the opposite of the linear coefficient, divide by 2 times the quadratic coefficient, which in this case we call A is 4 and B is going to be 6. So we'd say this is -6 over 2 times 4 is 8. That's going to be our axis of symmetry. We're going to see that come up again in some of the other things that we do in terms of solving stuff.
I agree. And if you wanted to find the y value of that vertex, if that's a future question, if you plug that x value in, you will find the answer.
It's true.
Let's see. I gotta move this over a little bit so I can read it. Use the given points to sketch possible solutions. This one says class. So this is going to be for them to try to figure out and then for us to talk about in class.
I like it.
So you just draw however many lines you can. Same thing.
Right, I'll jump back to this one. So you're going to draw as many lines as you can to kind of fit these things and do the best you can for that.
Yes, and then same idea on the next one, which Mr. Carlson already previewed for you because he's kind. And it says how many parabolas. So you want to draw your U's and figure out how many you can draw through each of those different scenarios.
Cool. All right. So this is kind of talking about the specifics of different forms of equations. And again, I'm going to slide that over a little bit so we can see a little bit better. And what characteristics we can really get at from each of these forms. Because different forms of equations are useful because they tell us different things. Standard form, which looks like this. An example of this would be something like 2x squared minus 5x plus 7.
I could find the y-intercept of that really easily.
Yeah, I was going to say, like, my favorite thing about standard form is that the y-intercept is really easy to find. How would you do that, Mr. Butterworth?
Well, the y-intercept is on the y-axis. And every point on the y-axis has an x value of 0. So I would plug in 0 for x, and that would get me what the y-intercept is, which conveniently in this case, if we're sitting in standard form, it's just that number hanging out, the plus 7.
Oh, so for our example, that would be a y-intercept that has a value of 7. It's whatever that constant number is, because there are no x's that would become 0 and cancel that part out.
The other piece you could get from standard form is what they're calling the concavity. That's the up or downness of the u. So because in Mr. Carlson's example, he put a 2 there, that's a positive number. So that means we're going to have a upwards u versus a downwards u.
So the positive means an upwards u.
Yes.
Cool. All right, how about factored form?
Factored form, well, that also has that a there in front, so that's that second one. And that a again tells you concavity. So you can tell concavity from factored form.
So if I had something like negative 2, x minus 3, x plus 5.
So since that has a negative leading coefficient, that would be a downwards u.
So that's a concavity thing again.
And you'd call that concave down.
Concave down. And that would make this one concave up?
Yes. You could find the y-intercept, but you'd have to work for it a little bit. So I think they're trying to say, what can we most easily find?
Yeah, I agree with that interpretation.
The other easy part would be the x-intercepts. So where the y-intercept is when x is 0, the x-intercept are when y is 0. So that's basically asking what makes that expression on the right 0.
Okay, and we had a shortcut that it looked like you used on the warm-up slide that had to do with each of these things.
Yeah, so basically the only way to make things that are being multiplied together equal to 0 is if one of them, at least one of them, is 0. So the negative 2 in this case we don't have to pay attention to because that's not 0. That's negative 2.
I agree.
But x minus 3 could be 0. And that's 0 when x is 3. And x plus 5 could be 0. And that's when x is negative 5. What did you write in the middle? Oh, is that an or?
I figured that it's nice to have x could be this or this.
Yeah, that's fine. I just couldn't read what it was.
Yeah, no worries.
Kind of looks like OJ. I don't know.
OJ is delicious.
What about vertex form?
So vertex form is my favorite form. I find it the most useful as far as knowing what these graphs look like. But it doesn't do a good job telling you some information. You know, I bet based on the name that our friends could guess what this might tell us really well.
I hope so. If they're asked to determine what vertex form could show, and given the choices, one of which is the vertex, fingers crossed they pick vertex.
This is really good at telling us the vertex. And the axis of symmetry, because I noticed that that's one of the words there too.
That's actually 3 words, but yes.
It's true. It's also good at telling us concavity. We have that A again out front.
But you're saying it's not so good at finding zeros?
Not so good at finding zeros. You got to do a lot of work there. But the vertex is really well identified for us right now. The vertex is going to be at the point h comma k, or if we had an example that was like -1/2, I know fractions are scary, x minus 4 squared minus 2. I also use 3 negatives in that one. The vertex would be at the point 4. We always do the opposite stuff for things that are inside our function. Things that are touching our x end up being the opposite value. And that's because we're looking for what trying to make that 0.
Yeah, that's what I was just going to say. I like to think of that as what makes that 0.
I do too. And then the y value would just be the number that's added to the end of the function. That's our vertex. Our axis of symmetry
is that x equals 4?
Is going to be at x equals 4. Look at you.
I'm good at this game.
And then concavity, we've got a negative out front, so we'd call that concave down. I'm just going to write CD because you don't know any other abbreviations that include CD because you're way too young.
True. They know what MP3s are though.
It's true.
Maybe. I don't know if even know if they know that now. What do we got here? Ooh, Christine and Kate. That's to determine the vertex of 2 different quadratic functions. Analyze their calculations. I moved it over so I could see it. So Christine looked at standard form. So that's standard form. Standard. So that means that was not, finding the vertex was not an easy thing to find from here. So they said, I know the axis of symmetry is at negative b over 2a, or the opposite of b over 2a. They said b was 12 and a was 2. 12 over 4 is negative 3. So that seems good. Now that I know the axis of symmetry, I can substitute into the function. So 3 squared is 9. 3 times 12 is 36. 18 minus 36 is negative 18. Yeah, that looks pretty good. I see nothing wrong there, which is good because it's a check mark.
Yeah, we were told that it was correct at the beginning. In fact, I think both of them are correct. Yep. Looking at Kate's work, she did this really similarly to how we found the axis of symmetry in the first one. She identified that this is in factored form and used that to find the x-intercept. So the opposites of each of these things that make each parenthesis 0. Just like we did, she found the average. She added them up, divided by 2. That's the middle, and got 2 as the answer for that. And then took that 2 and plugged it back in to get the vertex. I really like that both of them found the vertex in that way at the end, where they used different methods to get the x values, but then both of them plugged that in to find the y values. So that's kind of that's question A. How are they similar? How are they different? I like that I accidentally talked about that.
So you're saying they're similar because they did the same thing. Once they found the x value, they plugged back in to find the function value.
That's correct.
They're different because they're in different forms. So your strategy was different. Christine used a formula, negative b over 2a, and Kate could find the zeros from her form, and it had to go in the middle of the zeros. It says, what must Kate do to use Christine's method? Is that just that they have to multiply? She has to multiply it out?
Yeah, I think so. Because if you look at the difference between their methods, it's really from where they start. And for Kate to get to Christine's method, and we've done a bunch of multiplying like this before, where we do this double distribution to make it look like it's in standard form.
And then same idea for Christine, except backwards. So she would have to factor that function, which we may not be comfortable doing yet. But you could.
Cool. Sorry, the dog
Oh,
heard
more
noise.
Desmos fun. Oh, that's fine. We like the little puppy dogs.
It's true.
A Desmos activity. So they'll do that on their own.
I like it.
Analyze the graph. Circle the functions that could represent the graph.
Ooh, that's fun. So this is kind of looking at different characteristics that we have studied and trying to make sense of this. So I notice that you circled this one, and I would look at this one too, because I noticed that we have a negative out front. This is concave down, and I've got two factored pieces that both would have negative x-intercepts. And here I've got two negative x-intercepts. That's the only information I really have for this. So I think that works. I noticed you crossed out a whole bunch. They look like they all have things that are going on. Do you want to explain?
Yeah, so 3 of them are easy to explain. I'm not going to circle, so I'm not supposed to, but I'll recross them. F3, F4, and F5 all have positive leading coefficients, which I've now crossed out, so let me erase those. Those all have positive leading coefficients, so that would make the up u, or the concave up function. So those ones are off the table. And then F6 has a vertex, an x value of a vertex at 6, but the vertex of our graph is a negative.
I see that.
And F7 has an x-intercept at 3, but our x-intercepts are negative, as you just talked about. So that's why I crossed all of those out.
Cool. In looking at the one that we haven't kind of figured out yet, which is F2, and the first thing I want to say is that stuff in standard form is generally harder for us to figure out than the other forms.
In terms of graphically, definitely, yes.
Yeah, I don't really want to go there as far as finding the x-intercepts. That looks like an unpleasant thing for us to do, but I will talk about the vertex, and I'm going to use that formula because that's a faster way for us to kind of work with this right now, where x is going to be negative b over 2a, especially since we've used that a couple times so far. So that would be negative 3 over 2 times negative a third, which everybody's super happy to have a fraction over a fraction.
No, they go, ah!
It's fun because your mic cut out. I think you overwhelmed it with your yelling. Yeah, no, it's that's not our favorite thing to do in the world. I'll do the hard part. So negative 3 is positive 3. And then if I'm dividing that by what really is negative 2/3, that ends up being negative 9 over 2 is our answer. That makes sense to me based on the x value for the vertex. We also know this is a down parabola. The last thing to really make sense to me that I want to know is where that y value is. And I'm legitimately hoping that Butterworth was doing that while I was talking, but I don't think that he was because he's a jerk.
No, see, I intentionally did not do this problem because I didn't want to do all that work. So my first assumption was, yeah, it might work. And I think for this is just kind of a general idea of things. I think I would say, meh, sounds good.
Yeah, I think that's fair too, because even looking at the math that we're about to have to do, that's not pleasant.
No. But it looks like it will turn out, we want it to be positive.
Yeah, this looks like it's going to turn out pretty negative.
Yeah.
So my guess would be nay.
Nah, actually, I think it would be positive because you got 27 halves, which is like 13 and a half.
27 halves?
For the middle part.
Okay. And then if we do that, it's really going to be 54 fourths, and then minus 24 fourths.
Well, you did that differently than I was going to say you got 27 halves and 27 quarters, so you got 27 quarters. And and then 24 quarters. So it'll be a little bit positive.
Yeah.
The kids have totally tuned out at this point.
Oh, 100%. So now we're just playing a game to see who's still listening.
Yeah, like if you're still listening, shoot Mr. Carlson an email right now. Like right now, email him and say, I'm still listening, dude. But anyway, so yes, that one works. That was awful. So let's not I'm glad I skipped that one. Oh, we're supposed to circle it, I'm sorry. And then we didn't talk about F8, but I circled F8 because the vertex is at -6, 3, and it's a down parabola. So we learned a lesson. Standard form is terrible when we're talking about graphs.